After the anatomy and histology, let's talk about some normal thyroid physiology. Starting with the thyroid hormone. The synthesis of thyroid hormones is a complex multi-step process that occurs within the thyroid follicle unit. The process is dependent upon the presence of iodine and is outlined below. Follicular cells actively transport iodine and iron across the cell membrane from the bloodstream into the cytoplasm via the sodium iodine important membrane protein. The concentration of iodine within the follicular cells is normally many-fold higher than that of the systemic circulation due to its active transport. Iodide then moves towards the follicular cell border with the colloid stores, and the anions are oxidized to form the neutral iodine molecule. This form of iodine can pass through the cell membrane into the colloid. Colloid stores thyroglobulin, Tg, which contains a multitude of tyrosine residues. Colloid also contains the enzyme thyroid peroxidase, TPO, which catalyzes the next major step in thyroid hormone synthesis, which is the iodination of tyrosine residues on the thyroglobulin. A tyrosine residue iodinated by a single iodine molecule leads to the formation of the molecule monoiodotyrosine, and that iodinated by two iodine molecules leads to diiodotyrosine. The DIT and monoiodotyrosine molecules form covalent bonds with one another to constitute the active forms of thyroid hormone tetraiodothyronine or thyroxine T4, formed by two DITs and carrying four iodine molecules, and triiodothyronine T3, formed by a DIT and monoiodotyrosine and carrying three iodine molecules. When stimulated by thyroid stimulating hormone TSH, the follicular cells transport the active thyroid hormones from the colloid center into the bloodstream. Once in the bloodstream, greater than 99% of circulating thyroid hormones are bound to transport proteins such as albumin and T4 binding globulins. Less than 1% exists in free form. This allows a relatively tight degree of control of thyroid hormone diffusion into target cells in that the bound hormones will be released if circulating free levels decrease. Although there is normally a higher concentration of T4 compared to T3, T3 is the more potent form, and in fact many target organs such as brain, liver, gut, skeletal muscles, and thyroid are able to convert T4 to T3 through the deiodinase system that removes one of the iodine molecules. Iodine plays a primary role in thyroid hormone physiology, and it is predicated on there being an adequate supply in the body. The average daily iodine requirement for adult humans is 0.1 milligrams, and this is entirely derived from dietary intake. The thyroid is the target for the overwhelming majority of the body's iodine stores. Seafoods such as fish, shrimp, and seaweed are rich in iodine stores. Since 1924, the United States has iodized salt, which effectively has eliminated iodine deficiency in this country. Many regions of the world remains at risk for iodine deficiency despite worldwide efforts to improve access to iodized salt. The World Health Organization estimates that 54 countries remain iodine deficient. Thyroid hormone is critical for normal bodily function. On a cellular level, T4 and T3 bind to mitochondrial receptors, leading to increased ATP production, oxygen consumption, and glucose oxidation in a calorigenic process that releases heat. Therefore, thyroid hormone function is often referred to shorthand as the primary driver of the basal metabolic rate. It is hypothesized that virtually all cells in the body are end targets for thyroid hormone, mostly through their action with regard to stimulating lipid and carbohydrate metabolism. Thyroid hormone is critical for normal in utero and childhood growth and development, especially with respect to neurologic function. The cardiovascular system is an important target of thyroid hormone, which increases cardiac output and vasodilatation. Normal reproductive function is highly dependent on thyroid hormone. The regulation of thyroid hormone production is tightly controlled by interactions between the hypothalamus, pituitary, and thyroid glands. Low circulating levels of T4 and T3 stimulate the hypothalamus to release thyrotropin-releasing hormone, which in turn stimulates the release of TSH from the anterior pituitary. TSH stimulates the formation of thyroid hormones by binding to its receptor on the thyroid follicular cells, leading to both increased transport of iodine as well as transport and release of T4 and T3 from the colloid into the bloodstream. Conversely, elevated circulating thyroid hormone levels leads to a negative feedback loop with downregulation of thyrotropin-releasing hormone and TSH from the hypothalamus and pituitary respectively. Now let's talk about calcitonin. The thyroid gland also produces calcitonin from the parafollicular C cell, but the production of calcitonin is not regulated by the same processes that govern that of thyroid hormone. The primary known function of calcitonin is to decrease the serum concentration of calcium through its end action on bones by increasing osteoblast and decreasing osteoclast activity in the gut, by decreasing calcium absorption, and kidney by increasing urinary calcium excretion. And its release is stimulated by elevated serum calcium levels. However, the absence of calcitonin does not lead to a noticeable change in calcium homeostasis as it would for parathyroid hormone, and so its ultimate importance for normal physiologic function remains poorly understood.